From spectrum to molecular formula to structure. Dear students, today I am recording this lecture just to help you how to elucidate structure of a given compound on the basis of the spectral data, on the basis of the spectroscopic data. So here we want to go from mass spectrum to molecular formula and from molecular formula to structure. So this is simple. Many of the concepts that I am going to talk about today, we have already studied, okay? But I am making the things easy and simple, okay? So it is kind of making things easy, okay? So let's go ahead. Okay, what's this? This is a mass spectrum, okay? Now look at this mass spectrum. What do you see? Definitely you see peaks, and there are many peaks, okay? My question today is it possible for us to determine molecular formula on the basis of just this simple mass spectrum? The answer is no. Nowadays, we have another type of mass spectrometry that is known as high resolution mass spectrometry, or HRMS. And on the basis of that, taking into account all the isotopic masses, it is reasonably possible that from a high resolution mass spectrum, we predict the molecular formula of a compound. But from the ordinary mass spectra that we generally have, these mass spectra, we cannot determine the molecular formula unless we have other information with us, like what are the different elements present in this compound and how many atoms of each element present in this compound are there, okay? And similarly, other things like functional groups. What are the functional groups present in this molecule? And so on, okay? So on the basis of mere mass spectrum or simple mass spectrum or just mass spectrum, ordinary mass spectrum I mean, it's not possible, okay? But we have very important information here. This is the molecular ion peak, and this tells us the molecular mass, okay? So the question is, if we know the molecular mass and of course some other information, then can we elucidate the molecular formula of a compound? The answer is yes. Okay, let's see. Here, on this slide, we have some concepts which we have already gone through. For example, this HDI, or the hydrogen deficiency index, which is also known as degree of unsaturation or unsaturation number, etc. We already know this. What is HDI? What is its importance? How can we calculate it? Okay. If a hydrocarbon is saturated, that is, if it is an alkane, okay, then we know that it will have certain number of carbons, and because carbon forms 4 bonds, So there will certainly be a certain number of hydrogens. So we know that what is the general formula of alkanes. And if our compound has a carbon-carbon double bond, then of course for each double bond there will be 2 hydrogens less, and so on. And similarly, if we have a ring, a cycle in our compound, then for each cycle there will be 2 hydrogens less. So we already know this. Okay, so this slide gives us a general equation. So this is a general equation which we can use to calculate HDI for most of the compounds that we deal with in organic chemistry. Okay, so this is a very simple formula and you can easily apply it, use it, and calculate what? Calculate HDI. Suppose we have a compound whose molecular mass is 117 and molecular formula is this C8H7N. Okay, so we already know this molecular formula. So based on this molecular formula, how can we calculate HDI? So use this equation. Okay, so you have 2 and then multiplied by the number of carbons, which are 8 here, and then plus 2 from the formula, and then plus number of nitrogens. Here we have 1 nitrogen, so plus 1, then minus the number of hydrogens. We have 7 hydrogens here, and then minus X mean the halogens, number of halogen atoms. So here we don't have any, so minus 0. So you work up and you will find this answer. And you can have any other this type of the molecular formula and you can calculate HDI. Just remember one thing, if oxygen is present in your compound, just ignore it, okay? For example, you have this molecule C9H8O4, okay? And you are asked to calculate its HDI. Okay, how can you do it? Just use this formula, okay, and ignore oxygen. And when you will be doing this, you will be getting your HDI. So this is a simple way to calculate HDI, okay? And you should do a lot of practice so that you are well versed and strong in calculating HDI, okay? Okay, now here, don't be scared by this slide. A lot of things are written only because I want you to have everything in front of your eyes, okay? Here we have this data with us. We have a molecule and its mass spectrum shows a peak at 96, m over z 96. So that is the molecular mass of this substance. This substance has 1 carbon-carbon double bond and it also has 1 ring. So this is the data that we already know, okay? We already know that this is a compound, okay, having this types of things there. A ring is there, a carbon-carbon double bond is there, and its molecular ion peak appears at 96 m over z. So this is the data with us. Now, broadband decoupled C13 NMR spectrum is also given. What is broadband decoupled C13 spectrum. Broadband mean just the normal C13 spectrum. Okay, and depth 90 is also given, and depth 135 is also given. Okay, so this is the broadband decoupled C13 NMR spectrum. It gives us the carbons, all the carbons present in a molecule. When we say all, we actually mean all the sets of equivalent carbon, that is all kinds of carbons which are equivalent. So all the different sets of equivalent carbons. So we have how many peaks here in C13? 1, 2, 3, 4, and 5. So 5 peaks are there. Look at the chemical shifts values also. We already know that which range or which region of chemical shifts tell us what, which groups probably are present there, which carbon, which C13 carbon actually will be giving a signal in that region. So we know, and so keep the chemical shifts also in mind. Now, here, depth 90 gives no peaks. Okay, there are no peaks in depth 90. What does this mean? It means there is no CH group. There is no methine carbon in this molecule. Okay, no CH, no CH. Depth 135, no positive peaks. Negative peaks are here, here, and here, but no positive peaks. Now, in depth 135, which carbons give positive peak? Methine carbon and methyl carbon, yes. The carbons having odd number of hydrogens, methine and methyl. So, in this particular compound, the depth 135 says there is no positive peak. Means this molecule does not have a methyl group also. So it does not have a methine and it does not have a methyl. So it means we have other things. In the depth, we can only tell about those carbons which have protons, that is the protonated carbons, okay? The proton bearing carbons. So here are the proton bearing carbons. This, 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 and this. So it means they all are CH2s. They all are CH2s. Okay, if we compare these with this normal C13 spectral peaks, so what's the difference? Okay, which peak is absent here? Okay, here, yes, this one, 149.7. This peak is not appearing, this hasn't appeared in which? In depth. So which carbon does not appear in depth? Quaternary carbon, a carbon having no hydrogen. So it means this is such a compound which has no methine, no methyl, and has one quaternary carbon somewhere, the carbon having no hydrogen, and four methyl carbons, or 4 sets of methyl carbons, we can say this. Okay, so these are the data that we already have with us. And now, keeping all these things in mind, let's move ahead and see how can we solve this riddle. Okay, this puzzle, how can we solve it? Okay, it's easy. If we go step by step, okay, step by step, understanding each and every point, it's easy. Okay, don't be scared. It's just easy. Okay, we do not know its molecular formula. We know these things, but we don't know the molecular formula of this compound. So we have to determine it. How can we do this? So there is a rule called rule of 13. So here today, our focus is to learn this new thing, that is rule of 13. So what's the rule of 13? Rule of 13, okay. What's the atomic mass of carbon? Okay, 12. What's the atomic mass of hydrogen? 1. So this is how we have 13, the number 13, and we are now going today to learn rule of 13. Rule of 13. Organic compounds must have carbon. We know this, that all organic compounds have carbon. Mostly they also have hydrogen. Okay, so we can say that at least they have 1 carbon and 1 hydrogen, or any multiple of this, okay, any multiple of this. So we know the general formula of alkanes and alkynes also. So these are their general formulas. Okay, we already know these things. And now what we do? Rule of 13 is simple. Just what is the molecular mass of your compound? Okay, for example, A or B, or for example, in this particular compound, the molecular mass is 96. So what should we do? Just divide your molecular mass by 13. Okay, simple. Rule of 13 is simple. Divide your molecular mass by 13. And as a result, you will be having these things. You will be having a number that is known as a numerator, and you will be having another number that is the remainder. Okay, remainder. Okay, based on this, then your base formula will be this. Okay, possibly your molecular formula, but some more work we are going to do on this, and this is called base formula. Cn Hn plus R. What is N? N is the numerator, okay? When we divide the molecular mass of our compound by 13, we get a number and a remainder. This numerator number is N and the remainder is denoted by R, and this is just a simple formula, okay? Now, in our problem, we have molecular mass 96. So divide it by 13. You will be doing this, 96 divided by 13. So you will get then N is equal to 7. Remainder will be 5. So the possible molecular formula, or strictly speaking, the base formula will be this, okay? And so we have this C7H12, okay? Just simple. Molecular mass divided by 13, and you will be having a numerator and remainder. Just simple, okay? And use this formula, this one, okay? Remember from the data that our compound has a carbon-carbon double bond and a ring. This is the knowledge that we already have. Now, see what inference we can get from NMR, okay? Look at depth 90, okay? We have already talked about this. And then carefully study depth 135, and you will be getting certain information. Compare depth with broadband decoupled C13, and you will be getting another information. That is the information about what? About quaternary carbons. Okay, so C13 NMR shows 5 signals, but our molecule has 7 carbons. Okay, good. Okay, using this technique and this data, we have come to this formula, that is, it is having how many carbon? 7 carbons. But C13 broadband decoupled spectrum, this shows that there are 5 carbons. It means what? It means what? It means some carbons are equivalent. Some carbons are equivalent. Okay, so we have one quaternary carbon that is at 149.7 ppm. All other carbons are CH2s. One CH2 is very downfield, that is 106.9. Okay, and because our this compound has a carbon-carbon double bond, and because we do not have any CH and CH3s, and so the only possibility is that we should have this type of thing. This CH2 should be like this. So a doubly bonded carbon CH2. And this, if we have this CH2, which is very downfield, and this chemical shift shows that this is a carbon, that is the alkene carbon having protons with it. So this cannot be in a ring, okay? This CH2 having a double bond cannot be in a ring, because if there's a double bond in a ring, then the number of hydrogens that carbon can have maximum is 1. The carbon attached to it cannot be, and a carbon attached to this, this cannot be CH. Why? Because there is no CH in our compound. It cannot be CH2. Why? Because if CH2 is attached with this CH2, then that will be a separate compound. A separate compound. So only one possibility is there. That is, this CH2 is attached with a quaternary carbon. So here is a quaternary carbon. And so the quaternary carbon then will be attached with other carbons, and other carbons are only what? Only CH2s. CH2s. And so in this way, all those CH2s are bonded together, making a ring, and the quaternary carbon is bonded to this CH2 through this double bond here. So on the basis of all these considerations, one by one, using the rule of 13, finding out the molecular formula, the base formula and the molecular formula, and counting the number of carbons in C13 NMR spectrum, and comparing it with the depth spectras, okay, and ruling out the things one by one, and explaining our data, rationalizing our conclusions, ultimately we come to where? Okay, we come to where? Here. So this is the possible structure, okay? And you can see that it has this methylene carbon, which is very downfield. And here, this is the double bond, this is the quaternary carbon. And so this is how you can see the other CH2s. Okay, can you justify that these assignments are correct? Okay, I have done these assignments for you, and I want you to justify them. That is, have I assigned these values to these carbons correctly or not? Okay, this is you need to do. Okay, let's go into another example. A beautiful example, and we are going to do the same thing, that is using all that strategy and to determine the structure. Okay, this is a compound, this is the mass spectrum, and this mass spectrum has a molecular ion peak here, okay, and this also has a this base peak at 68, and there are other peaks as well, okay, but we know that we don't have to interpret each and every peak in a mass spectrum, okay. We just focus on the major peaks, and particularly the molecular ion peak and the base peak, okay. So we have this mass spectrum with us. We have this IR spectrum with us. And on the next page, we also have a, Proton Nmr spectrum and a C13 Nmr spectrum. So we will be going through these spectra one by one and trying to elucidate the structure of our compound. Okay, this is a compound whose mass spectrum is given to us, and in this mass spectrum we have this molecular ion peak, okay, and we don't have any other information except these spectra. Okay, look at the IR. Okay, what is the information that we can gather from IR? IR, okay, look at this peak. It's a very, very prominent peak here, and it is at 1685 per centimeter. Very prominent, very strong peak. This tells us that this compound has a carbonyl group. But carbonyl can be an aldehydic, carbonyl can be ketonic, carbonyl can be ester and an amide and carboxylic acid, etc. So we have carbonyl groups in many types of compounds. So which this, okay, look at this, and we are here to know that whether this carbonyl group is aldehydic or ketonic, or maybe it is a carbonyl of an ester or a carbonyl of a amide, etc., etc. Okay, what information do we have? Okay, here this part tells us that we do not have a carboxylic hydroxyl group. Okay, so carboxylic acid is ruled out. Do we have the possibility of having this amide? We know that amide carbonyl is present somewhere here, but in that case, we should have some other things in our molecule. Okay, for example, we should have what? We should have what? So amide mean we have a nitrogen, but what about this, the molecular ion peak in our compound? Is it even or odd? It is even. So most probably there is no nitrogen. Of course, there is no odd number of nitrogens, but the chances of even number is there. But because it is comparatively a small molecule, and we do not expect a nitrogen here in this molecule. So one possibility is that this molecule does not have a nitrogen, so this carbonyl is not an amide. Okay. This carbonyl cannot be an ester. Why? Because ester carbonyls are generally very here on the left at about 1700 40 or around that. So it is not that. So it means it is not an ester as well. What about an aldehyde? Okay, an aldehyde. So the quick test whether this is an aldehyde or not, we should go to the next spectrum, that is the which spectrum? Proton NMR. In proton NMR, here you can see we don't have a aldehydic proton, so it is not an aldehyde either. So what is the possibility? Okay, look at this peak. Okay, here you have this 3000, your demarcation line, a very important line. And on the left of this line, you have this important absorption, this signal, and this signal is because of carbon hydrogen stretching. Which carbon? sp2 hybridized. And if this is the correct assumption that we have made, then we should have a carbon-carbon stretching here, okay, at 1600 something, and so we have it. So it means that we have a carbon-carbon double bond also here, and that carbon-carbon double bond also, the doubly bonded carbon also has a hydrogen with it. Okay, carbon-carbon double bond is indicated by this peak, and sp2 carbon hydrogen double bond is indicated by this. And this carbonyl group, if it is ketonic, then this value is less for it, because generally the ketonic carbonyl appears at around 1710 per centimeter. But if it appears at a lower value, that indicates what? Conjugation. That is, that carbonyl is in conjugation with a carbon-carbon double bond. So based on these pieces of information, okay, we have now certain conclusions. That is, this molecule, whose molecular formula we don't know, but has this molecular mass, and this is such a compound which has carbon, which has hydrogens, and which also has oxygen. And that oxygen is most probably what? That oxygen is most probably a ketonic carbonyl oxygen, and that carbonyl is then in conjugation with a carbon-carbon double bond. So keeping this information in mind, and suppose now we can say that this is the molecular mass of a compound, and this compound has only one oxygen, so we can go this way. Since there is one oxygen, so 96 minus 16 is equal to 80. And 80 divided by 13, okay, that is what we are going to do is, we are now using the rule of 13. So we come to this, okay, and so n is equal to 6, r is equal to 2. Putting these values in our this formula, we have already learned in the previous slide, we get this. So this is what is our base formula, including oxygen into it. So we have this, our molecular formula. So this is the most probable or the possible molecular formula, C6H8O. Okay, so write these 6 and 8 as a subscript. Okay, now based on these informations, we can say that this is the molecular formula, but in this we have this type of the things, that is a carbonyl, and that is in conjugation with a carbon-carbon double bond. So this is the conclusion up till now, And let's go to the next and see what information we are getting from these NMR spectra. Okay, NMR spectra. NMR spectra is again very simple. This is our C13 and showing us depth values as well. Okay, so this is CH2, this is CH2, this is CH2. Okay, no CH3 here. This is CH, this is CH, and here we have a quaternary carbon. This quaternary carbon is because of the carbonyl, and then we have a carbon-carbon double bond having CH groups, and then we have CH2s bonded together, and so this is the knowledge that we can get from where? From the C13 NMR spectrum, okay, and the depth values. Okay, this is our what? Our proton NMR spectrum. Here you can see this is a CH2 and here we have two CH2s. Okay, we can say that this is a kind of triplet, but there a overlapping, this is an accidental overlapping of two CH2 groups here. They are two CH2 separate, two CH2 groups, but coincidentally they have almost not equal but very similar chemical shift values. And here we also have a CH and a CH, and these are in the form of a doublet, and this doublet is a doublet, and this is then further divided into other peaks. Other peaks mean it is doublet because of a nearby CH, but then that doublet is split up into a multiplet because that is attached to another group, that is CH2. So based on all these data, we can say that this is a molecule and it has this type of the bonding, and it has 1, 2, 3 CH2s, and then it also has 1 and 2 these CHs, and also has a carbonyl. Carbonyl is then bonded in a manner that you have this conjugation. So step by step, solving this puzzle, ultimately we come to this compound. So this is the structure of this compound, and so we followed the rule of 13 to elucidate its molecular formula, and then on the basis of the information that we get from mass spectrum, IR spectrum, C13 spectrum along with the depth, and proton NMR spectrum, and this is the structural formula of this compound. Okay, now let's go back and have another interesting thing. In the mass spectrum, the base peak is this. Now the question is, how can we explain the formation of this base peak, 68, okay, 68. So you subtract 68 from 96, and you will be getting something, and let's see how can we do this. Okay, this is how this ring breaks up, okay, and breaks up. This electron pair goes here, this electron pair goes here, this electron pair goes here, and as a result it breaks up, and we get this radical cation and this neutral molecule that is lost. Okay, the mass of this is 28. So when 28 goes out from 96, we get 68, and 68 is a very stable peak, very intense peak that is representing a very stable radical cation, and this is formed. This is formed because of this cleavage, and this cleavage is known as retro Diels-Alder reaction. retro-Diels Alder reactions. So remember that retro-Diels Alder reaction also occurs, if possible, in the ionization chamber of a mass spectrometer, and as a result, we get these peaks. So this is how we can explain the formation of this peak at MZ68. Okay, I hope that now you will be able to follow this types of the strategy and find out the structure of different compounds.